We press on now to part 7 of the endocrine system, page 612. And we're looking here at the kidney, and we're looking at the adrenal gland above the kidney. I want to take just a moment, since we've talked about some basic things. I want to say that at the very beginning of life, at the week 5 and 6 moments of life, that we actually have movement of the kidney, and I'll go over that developmental process at the end of this chapter, where the kidney rises from the pelvis and arrives at this location. Originally, the gonad is at this location, high in the abdominal cavity, up toward the diaphragm area where this is located. So we see it up here, high in the abdominal cavity. And the gonad is up here with this tissue. The gonad is a tissue that produces steroids. This cortex is a tissue which produces steroids. And the gonad is going to be traveling down starting from 5 or 6 weeks of gestation, just as the kidney is traveling up. So by the 8th week of gestation, the kidney has traveled up to this high spot, and the gonads have traveled down into the pelvis. Ultimately, the male gonad will continue and right before birth descend in the scrotum. So that's an important detail. First of all, though, let's take a look here at the two parts of the adrenal gland. We've already spoken about the medulla in the past, partly because we referenced the production of epinephrine. And epinephrine plays a specific role in the sympathetic system. The cortex actually is a steroid-producing tissue, and it has 3 general populations. And so let's take a look at that. We have here in the artistic rendition, and then here in the photomicrograph. I'm sorry that we have the opposite. This is the artistic rendition. This is the photomicrograph. We have medulla in here, cortex out here. The cortex has 3 portions. Zona glomerulosa on the outside, zona fasciculata in the middle here, and then closest to the medulla, but still in the cortex, is the zona reticularis. And we also have 3 populations of hormone-producing cells. Out here we have aldosterone, also known as a mineralocorticoid. Okay, and then we have cortisol, which is a glucocorticoid. Okay, and then here in the reticulata, we are going to be, or the zona reticularis, we're going to be producing the estrogen portions here. Actually, what's being identified here is the medulla. This is epinephrine, so I should be pointing with the E to this narrow band of tissue in through here. And so this would go like this. Okay, so let's make sure that we have that idea clear. This is a little acronym that I like to remember from outside to inside: ACE, ACE. It's in the direction of alphabetical order. So aldosterone out here, cortisol or cortisone here, and then the inclusion of estrogen and androgens and DHEA, other molecules that are precursors to the estrogens and androgens. Okay, so I have a little E right there. Estradiol would be a part of that program. There's a lot of, there's a whole family of female hormones, and then of course also the androgens. So then we come over here and we consider a particular idea. There's a cascade here that is something that we'll be visiting in 4 of the upcoming chapters before we finish the book. And so this is something that needs to become a normal part. One has to own this information. Let's take a look here that there are certain conditions that are unique to the human being before the invention of Safeway, I would say. One is that we have low blood volume and low blood pressure because our water supply is not great. And we also have low levels of sodium, just like every other mammal in the forest or meadow. Horses need a horse lick or a a sodium lick or a salt lick, any wild animal is going to be needing that. And to a certain extent, we were wild before the Neolithic period, so most of our existence as a species has been predicated on this particular issue, and our kidneys actually have not evolved. The only hot spots in our genome for evolutionary processes are two in number. One has to do with the ability to metabolize dairy products. Some adults have lactase, just as children do, to metabolize milk sugars, and we also have changes in skin color depending on latitude, distance from the equator, and whether or not we have direct sunlight. So long periods, thousands, tens of thousands of years in different locations result in different skin colors. Those are the only hot spots in the human genome. There are no others. And so we're all more or less the same family still at this point, because the family has not left Africa since, before 70,000 years ago, which is a very short period of time in evolution. So not much has happened. So our kidneys actually do kind of believe it's 50,000 years ago, and their entire chemistry is predicated on reversing low blood pressure, low blood volume, and getting more pressure in order to filter the blood. The purpose of the kidney is to filter the blood, and to do so anywhere from 40 to 60 times a day, so a lot of dialyses. And the result of the dialysis is that we empty the fluid portion of the blood into the kidney, and then we take back up again through absorption more or less what already happened in the duodenum and other parts of the small intestine. We take back up the water, the nutrients, and the electrolytes, and everything else ends up in the urine. Okay, so whenever there's not enough sodium, whenever there's not enough blood volume, then we're going to have to make adjustments here, and the kidney is good at that because the kidney needs blood pressure, big time. It's the most needy portion of the body in terms of blood pressure. So in the absence of good blood pressure, it releases renin. It activates a molecule through a number of changes, from angiotensin to, or rather angiotensinogen, which is already a molecule living in the blood from the liver, to angiotensin 1 and then angiotensin 2. It's a two-step process. And then eventually this comes over to the adrenal cortex, and as you recall, the outer part of the cortex has aldosterone, and so we get the release of aldosterone. Aldosterone has very specific actions in that it actually causes the body to pump sodium back into the interstitial fluid and into the blood capillaries that are nearby in the kidneys that are filtering. Right, so aldosterone is playing this important role. It's being exchanged, the sodium is being exchanged for potassium. So we need the sodium. What happens next is that water follows the sodium back into the interstitial fluids and into the blood. And so we retain this way our water component of blood, and we have scant urine as a result of that. So reabsorption of sodium, reabsorption of water, we exchange the sodium for potassium, so potassium is excreted, and that's partly of what's going on. Once we have enough water, hopefully we get inspired to drink some water as well, then we get what's called complete venous return to the heart. The heart is filled up with blood properly, no longer now at low blood volume, and we have, since we have a complete stroke volume, we get this special molecule that turns everything off that we just turned on. Since now we have good blood pressure, we produce this molecule called ANP, yet another hormone, atrial natriuretic peptide. And the situation here is that it's the rectification of the heart, getting more blood, a good stroke volume, and then the ANP goes out and rectifies everything and turns off the things that we just turned on. That's the cascade you must learn. for many future chapters.